Okay. We've been talking about the factors that influence sediment accumulation in the basins. We talked about the tectonic origin earlier in the semester. Now we are looking at the effects of a number of variables that influence the accumulation of sedimentation. And as we see as we go on tonight, we are talking about the combined effects of rates of subsidence, relative sea level change, and rates of sedimentation. And those are the three main variables that interact to give rise to the different packages that we see in the sedimentary basins. Obviously, various aspects of the sedimentary basins themselves impart a signature onto the sediment package as well. We talked about this briefly last time, the geometry of the basin and so on and so forth, related to its tectonic development. But these three other factors, these three variables, if you want to think of them that way, are particularly important in terms of determining thickness of the stratigraphic sequence, breaks in the stratigraphic sequence, these kinds of things that go on. And one of the things that we were talking about in class last time was the effects of climate in terms of large-scale sea level changes, and how obviously those sea level changes will influence the development of different packages of sediment. And most of you should be familiar by now with the fact that the planet has undergone multiple climate changes in the geologic past, but there are basically only two climatic states that the planet exists in, the icehouse climate and the greenhouse climate. And again, when we talk about things like denudation and the origin of sedimentary materials, we saw the importance of climate in terms of how that influences the origin of sediment. And as we see in this part of the class, the effects of climate change on the larger sedimentary package principally related to sea level changes, and principally many of those changes can be fairly rapid depending on climatic circumstances. So if we look at the icehouse climate and what characterizes the icehouse climate, and we are currently living in an icehouse climate. Obviously, we are living in a significant warm period within that icehouse climate, but nonetheless, the planet is still experiencing that large-scale climatic characterization. And the icehouse climate is characterized by strong latitudinal temperature gradients. In other words, when you go from the equator to the poles, there is a significant and major temperature gradient. Now, as we see when we look at the greenhouse climate, you similarly have a latitudinal temperature gradient. It's going to be warmer at the poles, at the equator than at the poles, obviously, but the significance or the extent of the gradient of that change is significantly different. Again, as you might imagine, you have low mean ocean temperatures in the icehouse climate, and this in part then leads to very active, strong active oceanic convection, where surface waters are heated and you have waters near the poles cooling and subsiding, and this drives a very active oceanic convection system, which has the effect of giving rise to highly oxygenated oceans, so that deep ocean waters are reasonably well oxygenated because of the very active convective circulation patterns driven by these icehouse climatic conditions. And of course, perhaps most convincingly, in terms of identifying the climatic state, the presence of significant continental ice caps and sea ice. Sea ice obviously in the Arctic and the Antarctic continental ice cap that we saw in our discussion in class last time. So those are the principal characteristics of an icehouse climate. And as you can imagine, when you flip to the greenhouse climate, you essentially see the reverse. You have weak latitudinal temperature gradients. So there is a temperature difference, obviously, between the equators and the poles, but the extent of that difference is somewhat diminished. The ocean water temperatures are going to be significantly higher, obviously, and because you don't have the temperature contrast developed in the world's oceans, you don't have the same degree of oceanic circulation. And in fact, ocean circulation gets to be quite sluggish during the greenhouse climate, and this leads to anoxic marine conditions because the oxygenation of the waters at the atmosphere-ocean contact is important, obviously, for the absorption of oxygen. If you then take that water and circulate it vigorously throughout the system, that oxygenated water gets to the deep ocean and other places in the ocean basins, giving rise to conditions that, one, affect, obviously, the organisms that live there, and two, they affect the sediments that accumulate. So a lot of the black shales, for example, that we see in the stratigraphic record, if you look at the Phanerozoic as an example of stratcolumn of Phanerozoic, which we will a little bit later on, and you look at the distribution of black shales, you see that it's no accident that significant thicknesses of black shales exist or were deposited during times of the greenhouse climate, and they represent the trapping of significant amounts of organic material because of the anoxia that existed at the time of their deposition. And then, of course, finally, and quite logically, you have warm polar regions and you have no ice, sea ice or ice caps. And this gets into some interesting discussions in detail because I know in talking with Dr. Bhattacharya, there are arguments about there being brief periods of glaciation during the Cretaceous, for example. This is indicated by some stratigraphic information that they've got, but there is no record, no consistent record that I know of that would suggest the strong evidence in favor of icy conditions during the Cretaceous. But so whether or not there are relatively small scale, I'm talking here in a time scale sense here, little excursions where you get cooler periods. We had the Little Ice Age in the northern hemisphere, which lasted 400 to 600 years or whatever it was in the 17th and 18th centuries, I think it was. So we know that looking at shorter time intervals, that there are excursions to warmer and colder intervals. But the large-scale picture obviously is tied to these two major climatic conditions. So then you get into the question of why does the climate change? The dinosaurs didn't drive around in SUVs, and so you can't blame the SUVs for global warming in the Cretaceous. So clearly there are natural phenomena at play here that drive the climate one way or the other. And what we are seeing today, of course, is anthropogenic driving of the climate because we are taking the sediments that were deposited in the anoxic conditions of past greenhouse climates, and we are releasing that carbon dioxide by burning the oil and coal and the other preserved organic material. So if we look at kind of general causes for climate change, there are astronomical variations, changes in the nature of the Earth's surface, and this is kind of a plate tectonic explanation, if you like, related to the accumulation of supercontinents and superoceans versus dispersed continents and relatively smaller oceans, although their total surface area doesn't change significantly. In other words, about 70% of the world through the Paleozoic was oceanic and 20-25% continental. But depending on how you clump the continents together or break them apart, you obviously change the nature of the Earth's surface when you do that. And then, perhaps more interestingly from our perspective today, changes in atmospheric composition is a major player in the climate game. So if we look at astronomical variations to explain some aspects of climate variation, I'm not quite sure where they get this information from, but the argument is that there is a change in the frequency and or intensity of the solar radiation flux. In other words, the amount of energy coming from the sun. And the argument is that there has been a change over time, and that the change is dominantly in one direction, and that is an increase in the solar radiation reaching the planet on the order of about 1% per 80 million years. And that presumably is tied to the evolution of the sun itself. These things are supposed to burn out over however many billions of years they last. And so whether that is a relatively linear process or whether fluctuations in that, I don't know. But certainly solar radiation would be an important component of any astronomical variation we might see. But more likely and somewhat easier to recognize smaller scale orbital perturbations in the planet with respect to where the planet is with regard to the sun, because the sun being the principal source of energy, at least on the surface of the planet, that's important. So if the Earth was orbiting the sun for example, in a perfectly circular orbit, and the planet itself was orbiting orthogonal to the plane of the orbit around the sun, in other words, if the planet wasn't tilted, then a lot of the kind of variation that we are talking about here related to orbital perturbations wouldn't apply, and you would have a much more constant climatic situation than we observe, and that is the variation that we do see is in fact tied to the fact that the planet does not orbit in a perfect fashion around the sun. So if we look at these different parameters that can influence climate, there are three orbital variation patterns that we see. Eccentricity, on the upper diagram there, essentially relates to whether or not the planet orbits the sun in a perfectly circular motion, and the fact is it doesn't. The orbit is slightly eccentric. The second characteristic is the obliquity characteristic, and that has to do with the fact that the Earth is orbiting about its axis, its rotational axis, and that rotational axis is tilted with respect to the plane of the rotation around the sun. And that has an influence. And finally, precession that tilting of the planet about its rotational axis essentially wobbles. And that's what precession is, and that wobbling makes a difference. Now, how does this work? Well, what all of these things mean in reality is because of these little perturbations and these differences at different times under different circumstances, the planet or parts of the planet will be either closer to or further away from the sun. Now, the difference in terms of total number of kilometers is probably not that great, but the fact is those differences are sufficiently are of a sufficient magnitude that the amount of solar radiation received by the planet or the part of the planet that is either closer or further away from the sun makes a difference in terms of the climate. And you'll notice on here there are cycles labeled under eccentricity, for example, 95,000 years, 123,000, and 413,000 years, because these things, the irregularity of the orbital parameters that we are talking about here are in and of themselves predictable, so that they will occur at a certain cyclic rate, and so obliquity has a 41,000 year cycle, precession has a 19,000 and a 23,000 year cycle associated with it. And on the left there you have the three, the electricity, the obliquity, and the precession, showing you how these things vary. And let me get the pen activated here. The upper part of the diagram up here is a measure of the ellipticity, the obliquity, and the precession, and you see that these occur in a cyclic fashion, and they measure the insolation effect of those cycles measured in watts per square meter. That's the energy level that you measure. And so each of these parameters has its own cyclicity, obviously, and obviously they interact with each other, either reinforcing or cancelling each other out. And the end product, which is B, okay, is the combined effects of those three orbital parameters expressed in terms of temperature, watts per square meter, either higher or lower wattage per square meter, depending on whether the combined effects are moving part of the planet away from the sun or closer to the sun. So, if you're familiar at all with astronomical texts on climate, you will see them in terms of Milankovitch cycles. People talk about Milankovitch cycles. Those are related to these kind of orbital parameters. The second factor that can influence the climate is the change in the nature of the Earth's surface. And I don't know that bullet there is correct in the sense of changes in the total area of land. The total area of land will vary, of course, because if you flood the land, you cover it with parts with water. But the overall continental versus oceanic relationship on the surface of the planet, certainly through the Paleozoic, probably has not changed much. In other words, the 70, 75%, 25, 30% continent, 70, 75% water hasn't changed. So clearly, during times of high stands of sea level, mostly related to the change in volume of the mid-ocean ridges that we talked about in class on Monday, will affect the total area of land that's exposed. and that's the reason why exposure of the Earth's crust is important will be made clear a little bit later. So it's probably more important to think of this in terms of the geometry and distribution of ocean basins and continents, and how that affects ocean circulation patterns. The ocean, the world's oceans are extremely important, obviously, in affecting the climate, because the circulation of water through the world's oceans is a means of distributing thermal differences by virtue of water circulation. And the example that I mentioned very early on in the semester, when we were or earlier on in the semester, when we were talking about denudation and uplift and erosion and all that kind of stuff, was changes in elevation and disposition of orogenic belts. And the examples we talked about were the Himalayas, in which I pointed out that the Himalayan front ranges of the Himalayas today form such an impressive barrier to atmospheric circulation that you have this major climatic condition in the subcontinent of India known as the monsoon period. And the monsoon is essentially tied to the air circulation patterns that essentially the warm, moist air of the Indian Ocean moving north over India hits that almost vertical wall of the front of the Himalayas, forcing the moist, warm air upwards and causing it to drop its moisture and giving you the torrential rain of the monsoon season. And clearly that has a major influence on various of the geologic processes that we've been talking about, weathering, erosion, those kinds of things. So not only is the disposition of continents and ocean basins and the geometry of the ocean basins important because it influences oceanic circulation. Imagine what would happen in the world today if we were to remove the Isthmus of Panama. In other words, if we were to open a link between the Atlantic, Caribbean, and the Pacific. There would be significant changes in ocean circulation patterns if that were to occur, and that would have a significant effect on weather in general and climate in particular. So ocean circulation is important, but atmospheric circulation can also be influenced by changes in the nature of the Earth's surface, which is what the kind of the title of the slide addresses. So the third kind of explanation for climate change is atmospheric composition, and obviously we're here talking about greenhouse gases. The greenhouse climatic effect was first recognized in the late 19th century, so it's not a kind of a recent concept that's been developed or recognized. We've known about it for well over 100 years at this point. I've got two greenhouse gases listed here, carbon dioxide and water vapor. I could, of course, add that there are other greenhouse gases, the most notable of which I don't have listed is methane. And methane, it turns out, is ironically is a more effective greenhouse gas than carbon dioxide, but it has a much shorter residence time in the atmosphere. Carbon dioxide has a fairly long residence time. It's hard to calculate, but meteorologists will talk about 100 to 200 years, that sort of thing. So, and that's important, obviously, because people talk about reducing the amount of carbon dioxide we put into the atmosphere. That's probably true. But what we are putting into the atmosphere today is going to be there for quite a while. Methane cycles through a lot quicker, apparently. But when it's there, it's a very effective greenhouse gas. And I noticed the other day there was a report in the paper that the Japanese had made the first successful exploitation of these things called clathrates or hydrates. These are these methane deposits, frozen methane deposits that you find in the sediments of North America, of Japan, and of many other continents. There is a huge reservoir of methane apparently frozen in the sediments of the world's oceans. And one of the great fears of trying to exploit that resource is you could start a runaway process where you start to produce the methane and then it would be kind of a self-sustaining activity. Whether that will occur or not, I don't know, but if it does, it would be pretty catastrophic in terms of changing the composition of the atmosphere. So we'll kind of stick to a discussion on these two gases primarily to see how it is that they influence climate. Well, because the argument is, and it's true of any greenhouse gas, but obviously is the same for carbon dioxide, if you have a rise in CO2 in the atmosphere, that will cause, because of the greenhouse effect, the temperature of the atmosphere becoming somewhat warmer. When that occurs, the atmosphere is capable of holding more water vapor in the atmosphere, and water vapor itself is a greenhouse gas, so it becomes a kind of almost like a self-exciting system when that happens. So, and if you look at some numbers that people like to throw around, if you take the present day concentration of carbon dioxide in the atmosphere, which I think is at its highest level for 800,000 years was the number I was just looking at, but it's pretty high. If you were to cut that in half somehow, it would cause the worldwide average temperature to drop by about 4 degrees Celsius. On the other side of the coin, which is more likely than the first point that I made there, if we were to double the CO2 concentration in the atmosphere, you would increase average temperatures by about 8 or 9 degrees Celsius. And here, remember, we are talking about average temperatures. I mean, so you figure 8 degrees, it's 80 degrees out, what's the difference? 80, 88 is no big deal, it's just a little bit warmer. But these are average temperatures. So that gets to be a real major issue, obviously, in terms of the effect on climate. So the obvious question then is, if these greenhouse gases are players in the game of modifying and altering our climate, what changes CO2 concentrations in the atmosphere? Well, today, of course, you only have to look out the window and you can see why, because you have cars burning fossil fuel, or any fossil fuel that you burn, gas, oil, coal, or whatever, you're going to release what I like to call paleo solar energy into the atmosphere. But as I pointed out, the dinosaurs didn't have SUVs, so there must be other reasons why the CO2 concentration changes. And you get into a very interesting debate at this point, because there are arguably two sources of carbon in the carbon dioxide system, one related to the organic side of the equation, and the other one on the inorganic side of the equation. Some people believe that the organic carbon dioxide cycle is essentially balanced, roughly balanced anyway. And so plants are effective in fixing carbon into biomass, obviously, through the process of photosynthesis. And so they're, on the one hand, they're sucking carbon out of the system. But of course, when the plant dies and decomposes, you put the CO2 and the associated carbon, obviously, back into the system. And the point that I was making earlier about black shales, about coal, about oil, that represents undecomposed carbon, as it were, that was generated in the past, that those accumulations of material didn't undergo the oxidation process to destroy that material. And by virtue of burning that stuff today, we are doing what may have happened or could have happened millions of years ago, but now it's being generated today. If we accept that middle bullet there as being approximately correct, and I don't know if it is or it isn't, but that's an argument put forward by some people. If that's correct, then the bulk of the CO2 variation that you might see historically that influences climate may well be related to the inorganic carbon dioxide cycle. In other words, carbon dioxide generated by, for example, igneous activity. So, in looking at variations in carbon dioxide in the atmosphere, which obviously influence climate, temperature, and so on and so forth, we can look for increased sources of carbon dioxide. Well, one way we could do that is have increased plate tectonic activity. That will result in, we're back to the argument about rates of seafloor spreading. As we saw when we talked about the change in volumes of the mid-ocean ridges on Monday, an increase in the spreading rates associated with divergent plate margins results in a larger volume of the mid-ocean ridge, and that's because there's been a change in the rate of seafloor spreading, which is a measure of plate tectonic activity, obviously. So the argument is you increase volcanic activity in the plate tectonic realm, and that generates mantle-derived CO2 that's given off. That increase in carbon dioxide in the atmosphere causes the atmosphere to warm. That results in higher stands of sea level because you're either heating the water, and as I pointed out last time, that will give you increased volume, will give you higher sea levels, and also obviously higher temperatures are going to melt any ice caps that you've got, and that obviously will contribute to higher stands of sea level, flooding the continents, if you will. And the reason why that's important is if when that happens, the increased sea level flooding the lands covers a certain amount of the land area, so you diminish the amount of the continents that are exposed to the weathering process. And the reason why that's important is the weathering process is one that sucks up carbon dioxide. So if you reduce the amount of weathering, you are reducing the amount of carbon dioxide that you're taking out of the system. Combine that with the increased production of carbon dioxide associated with volcanic activity, and you see the potential cause here of global warming related to increased carbon dioxide in the atmosphere. And when you look at the I don't know if I think we looked at this diagram earlier, but basically what it shows is sea level changes. There are two different sea level curves you see here, this representing high, this representing low. The curves are somewhat different again because the assumptions made in the models that were used to derive these curves are somewhat different, but also plotted on this is volcanic activity. Now, volcanic activity in this case is measured by looking at volumes of protons, because of course the surface expression of volcanic activity, volcanoes and lava flows and things like that, tend to be destroyed through weathering and erosion, but at depth beneath volcanic arcs and things of that kind, you have plutonic bodies that are formed, and the measure of plutonic bodies is what gives rise to this part of the diagram right here. And you'll notice, of course, that when you have increased volcanic activity, you have higher stands of sea level. And when you have higher stands of sea level, you are sitting in a greenhouse climate. You see there and there. In part, the argument is that it's greenhouse because of the change in the composition of the atmosphere. And when you have lowered amounts of igneous activity, you have lowered sea level because you're not putting as much CO2 into the system. That results in a cooling of the planet. Cooling of the planet results in the sea level dropping. Sea level drops. It exposes more land area. You have more weathering. Weathering is a carbon dioxide sink. So now you're not producing as much CO2 and you're sucking more of it out of the system, and you get into a icehouse climate, the ice house. Here's an interesting excursion right here in the middle of the Paleozoic. In the late Ordovician, there's evidence to suggest that for whatever reason there was a cooling interval in the middle of that large extent of greenhouse climate. So here are the sinks. You have decreased plate tectonic activity as marked by decreased amounts of volcanism. You're not producing as much CO2. That results in cooling, lowering of the sea level, exposing more land area, increased weathering, big sponge sink, whatever you want to call it, sucking carbon dioxide out of the system. This is kind of the good news, bad news side of this story is that this appears, at least at some level over the last 5 to 600 million, 5 to 600 million years, that there is a built-in control to the system. In other words, once you start warming or cooling, why don't you just keep going? And this is the argument as to what happened on Mars, of course, is that it had climatic cycles and it got into a warming period and the warming just kept going and it just dried the planet and the water evaporated or got taken up by minerals or whatever, and so the planet literally died. People point out, at least on this planet, for the last 600 million years at least, as it's got colder or warmer, it's kind of reached some kind of a tipping point and flipped back in the other direction. So that in the long-term sense is the good news. From our perspective, it doesn't make much difference because none of us can be around long enough to find out if the current warming cycle is going to keep going or tail off. Okay, so those are some of the kind of, I would say, natural causes. By definition, it's natural. Some of the causes for climate change. And if we look at the Phanerozoic, the most recent 600 million years or so of Earth history, we see that there are cycles of Eustace volcanism and climate change that exhibit a first-order periodicity of about 300 million years. And these are what people refer to as first-order cycles or first-order patterns or whatever you want to call them. And why these exist? It may be related to plate tectonic activity, ironically. Because as we've seen, it's the igneous activity that might be the source of carbon dioxide, the flooding of the continents, the reducing the weathering process. So it's kind of interesting that the surface conditions of the planet, the climate, if you will, may well be largely controlled by the solid Earth and its behavior in terms of producing these climatic changes. And so if we look at this on a first order scale, here's the Phanerozoic. Here is the sea level cycle. This is obviously high on this side, low on that side. And of course, when you look at the periods of high stands of sea level, you're dealing with a greenhouse climate. And when you're looking at low stands of sea level, you're looking at icehouse climates. Okay? And you can see black shale formation indicated in association with greenhouse climates. And that's because of the characteristics we talked about the different climates, the poor ocean circulation and anoxic conditions. And the other thing that you see, of course, is in a tectonic sense, you have two major events. You have the breakup of Pan-Africa, which is one of the early supercontinents. And interestingly, prior to this time, this is when you had Snowball Earth was, I think, what, 680 million years or thereabouts. Snowball Earth is interesting because that was a situation in which the entire planet is theorized to have been covered by ice. So you had sea ice over the world's oceans, not only in the polar regions, but in the non-polar regions, and certainly significant ice caps on all the continents. And something happened, and it may be, of course, that the breakup of Pan-Africa is what changed that, because when you break up Pan-Africa, that implies tectonic activity, igneous activity. As you break up the continents, you get new oceanic lithosphere form. That's related to volcanic activity, CO2 being pumped out, and so on and so forth. So it may be that this was the kind of the breaking of a long cold cycle. And then, of course, you have the growth of new supercontinents, Pangaea particularly. And, of course, you have low sea levels, icehouse climatic conditions. You break up Pangaea, which we've talked about, the breakup, particularly we looked in the Atlantic, as examples of extension and so on and so forth. And lo and behold, again, you're dealing with more plate tectonic activity and how this then may tie to these climatic changes. And the interesting thing about this, of course, is when you look at this, these events that change climate involve things like regressions and transgressions. And from the stratigraphy, sedimentological point of view, on the large scale at least, a lot of what we see preserved in the stratigraphic record is tied to this larger picture of tectonic activity and how that tectonic activity influences climate and how the climate influences the packages of sedimentary rocks that are generated and so on and so forth. So over the last 600 million years, then we have essentially a bimodal distribution of sea level, high standards of sea level during the middle part of the Paleozoic and the Cretaceous through the Oligocene related to greenhouse climate, obviously, and then low sea levels during the late Precambrian, the late Paleozoic, the Mesozoic, and the Oligocene to present. So we are living in, I would say, in an interglacial period of an icehouse climate. And there's this diagram again that essentially summarizes that. The upper part of this diagram, which I'm not going to talk about particularly, has to do with biotic crises, extinctions, if you will. Some of them are quite obvious. This is the Cretaceous tertiary boundary that most people tie to extraterrestrial impact objects. There's increasing evidence to suggest that probably wasn't the proximal cause, but more the straw that broke the camel's back type of thing. And if you want to tie biotic crises, the end of the Permian, the Permo-Triassic extinction, the biggest of the 6 Phanerozoic extinctions, tying them to climatic change is tricky simply because when you think about extinctions, you think about them being relatively rapid, and climate change may not be rapid enough to accommodate those kinds of things. But certainly when you look at biotic crises, extinctions, climate is obviously an important factor for the biosphere. So the biosphere will interact obviously with the solid earth at that point. And if you look at biotic crises, everybody always looks for the smoking gun, the silver bullet, or what have you. And of course, the impact theory of the Cretaceous Tertiary event just has this wonderfully appealing effect because it's simple and clean. So it turns out that if you start reading more detail about that extinction event, the detailed stratigraphy makes it look more and more likely that the event certainly occurred, because you've got the crater and all that kind of stuff. But the perturbation that it caused in the environment was the kind of the final stroke that did the damage to much of the biosphere, rather than the proximal cause. So we have these very large-scale cycles that may be tied to the large-scale effects of plate tectonics and how that plays. But when you look at these cycles, you recognize they're not smooth. There are smaller cycles superimposed on the larger cycles. This is like when you look at the stock market index. Stock market doesn't go up and it doesn't go down. It goes up and down, up and down, up and down to a high point, and then it goes up and down, up and down, up and down to a low point. Well, these climatic cycles or oscillations are similarly inclined. You have the first order cycles that had a 300 million year duration to them. Second order cycles, known as super cycles, have a duration of about 10 to 80 million years, that range, ballpark range. You have third order cycles, 1 to 10 million years, and then you have fourth order cycles, which from a detailed stratigraphic point of view are interesting, because it is at this level that you see the Milankovitch cycles coming into play, because here we are talking about cycles that are on the order of tens of thousands of years in terms of their periodicity. And again, you can look at this, you've seen diagrams like this. This is obviously the Phanerozoic starting down here in the Cambrian. Here are your major cycles, the first order cycles shown here, and this diagram also shows the second order cycles or super cycles, where you can see variations, if you will, on the first order. This is an old diagram. This kind of very sharp drop that you see there is now recognized to be an artifact of sampling and measuring. And I think the next diagram shows, well, it's still pretty steep, because the changes are considerable, but they tended to round them a little bit more in terms of the rapidity with which they occur. And then, like the first cycle of the previous slide, you see the first order cycles right here, second order cycles right there, and you see some global tectonic information, if you like, in this column. The breakup of Pangaea and the generation of Pangaea, maximum dispersal of continents early in the Paleozoic, and the breakup of the supercontinent Pan-African mass in the late Precambrian. And then you've got the different climatic stages shown in there like that. And these are the major sequence stratigraphy cycles that were recognized in the 1950s and 1960s, I think it was, by a number of people related to flooding transgressions and unflooding regressions on the North American continent. So if we look at smaller scale cycles and we concern ourselves with the factors that come into play to give rise to these packages of sediment, we look at the interactions between relative sea level changes, rising or falling, subsidence or uplift, which is for the most part obviously a tectonic product of tectonic actions and interactions, and sediment accumulation rates. Now you would think that when you look at a system in which you have three variables, how hard could it be to kind of get a picture out of that when it turns out to be really quite messy. The stuff that I'm going to be talking about right here is in chapter 7 of your textbook, and I encourage you to go read that chapter and spend some time looking at these diagrams. Because what he does here is he looks at the change in sedimentation. Obviously here you're looking at an increase in sedimentation. Here he's looking at change of, in this case, vertical motions in the form of subsidence, and he also talks in terms of the static effects, if you like, sea level fall and sea level rise. And depending on how you have these three different factors interact, you can have significant changes in sea level, you can have significant changes in water depth. That's what we use in this situation. Here, for example, you show subsidence occurring at this rate and sea level falling at the same time as you have subsidence. And because subsidence outstrips sea level fall, you still generate accommodation space. In this case, where you've got sea level rise being significantly greater than subsidence, you can have obviously have sea level rise and water depth changes. So like I say, go to chapter 7 and look at these kinds of diagrams and read about them in detail, but basically what they're attempting to do is to make you think in terms of how sea level changes, sedimentation rate changes, and vertical changes, uplift and subsidence, influence the stratigraphic package that's going to develop in a sedimentary basin. So what he tries to do in these diagrams is he's trying to get a handle on the three variables. So for example, in the upper diagram there, what he's done is he's held subsidence as constant, or as a constant, and sediment supply are constant. The only thing changing in that upper diagram is eustatic sea level. And he shows it in a very cyclic sense, where you go from relatively low to high, back to low, back to high. And this curve, right, or this line right here, represents the constant subsidence. This represents sedimentation. And what happens is when sea level is rising on the curve, and you combine that with subsidence, you are generating accommodation space. But once you pass the peak of the sea level rise and you begin to cause sea level to fall, and you keep obviously subsidence sedimentation the same, at some point what's happening is you are losing accommodation space in that circumstance. Let me see. Okay, the second example that he looks at is you keep sediment supply and sea level constant. In other words, sea level is not going up or down. The supply of sediment is constant, but now we are changing the subsidence. So you have a relatively low rate of subsidence and then significant increase, slow increase, slow increase. And what happens is, in that process, in terms of accommodation space, you're either generating a little bit of accommodation, certainly when you have a significant amount of subsidence, or when your subsidence essentially is constant or ceases there with a uniform sea level, you are going to have shallowing because the sediments will accumulate and fill the accommodation space. And at some point, you will get the situation at the end of this fairly constant state of no subsidence, where the accommodation space is destroyed or filled. It's not being destroyed, it's being filled by sediment. And when that happens, you've got to do something about it, and typically you're talking about sediment bypass systems kicking in. And then the last example that I've got on here is we keep subsidence and sea level constant, but we vary the sediment supply. And so, again, very much like in B, what happens is when you vary the sediment supply, you increase or decrease the sediment supply. You either overwhelm the accommodation space, or if you have very low rates of sediment being in, obviously the accommodation space is more than capable of accommodating the sediment being generated. As a kind of a further complication to this picture, and that's why I encourage you to read this chapter in the book, because you've got to look at these for a while to figure out what's going on. What he's done here is he's kept subsidence rates and sediment supply rates constant, and he's allowed sea level changes to occur. But what he's done is he is allowing the frequency of the sea level change to vary. So, for example, in A there, you have a low to medium frequency sea level change. And what happens is, again, this line represents the constant subsidence. This kind of vertical line here represents the constant sediment supply. And here we have sea level very, very slowly increasing and then decreasing. So at this point, you generate the most accommodation space. At this point, you are not being very successful in generating accommodation space. So if you go to the middle diagram where you've got a medium frequency change in sea level, and you have the constant sedimentation rate, you see that you develop breaks in the stratigraphic record, because with sea level rising here and constant subsidence and a fixed amount of sediment, you are generating enough space, accommodation space, to accommodate the sediment. But once you get to this point and you begin to decrease sea level, at some point you're going to end up exposing material. You're going to slowly decrease the amount of accommodation space. Sedimentation more effectively fills it, and at the point that you fill the accommodation space, the region is going to experience erosion, and you're going to lose sedimentary material, so you get erosion occurring and loss of accommodation space. And when you get erosion occurring, you end up getting hiatuses shown in of different lengths, obviously. Area 2, the erosion doesn't kick in until this point. Area 3, it kicks in a little bit earlier. See, so here's the erosion cutting deeper and deeper as you go down the system. And then obviously you've got a high frequency sea level change in sea, and you have much more erosion going on than deposition and accumulation. So you're going to have large-scale erosional unconformities developed in that system. The point of this is to point out to you that, again, when you look at an outcrop in the field, you have to ask yourself the question: what's going on in terms of why am I seeing these kinds of thicknesses? Why am I seeing unconformities? Why am I seeing breaks in the record? And it's tied to the interaction of these three factors. Now, you'll notice in trying to deal with this, he does what is a very simplistic thing. He holds two things constant and allows one to vary. Well, Mother Nature is not that accommodating, because Mother Nature will change sedimentation rates, will change sea level, changes in sea level, and change rates of subsidence. So when you have the three of them all acting together, you can see how complicated it can get. So when you look at the development of stratigraphic packages, you're looking at elements of sequence stratigraphy, obviously. And sequence stratigraphy typically looks at packages of sedimentary rocks that were deposited during a single cycle of sea level change. And this is the classic picture of change of sea level, where you have an amplitude and a cycle period, obviously, this being a half cycle, and you have these things called inflection points, and these represent where you have the greatest change of either generation or destruction of accommodation, shown by the relative length on these axes. So the inflection point here represents the point in the cycle where you see the greatest amount of accommodation space being generated, and on the downside, that's the point of the greatest loss of accommodation space. So obviously, the interaction of these various factors give rise to transgressions and regressions, and as most of you know or should know at this point, what the definition of a transgression and regression is. Transgression is a change in the location of the shoreline. There's nothing to do with rising sea level or falling sea level. Well, it has something to do with rising or falling sea level, but it is the movement of the shoreline. If the shoreline moves towards the continent, that's a transgression, however that's caused. Because you could have subsidence of the continent occurring faster than lowering of sea level. And when you combine those two things, you end up with a transgression, even though sea level is falling. Okay. And similarly, that would be, well, a forced regression will occur, even if you hold the continent with no subsidence or uplift. If you have a rapid fall of sea level, that will generate a forced regression. It's called a forced regression. And so the regression, by definition, then, is the movement of the shoreline away from, or towards the ocean, or towards the body of water, and away from the continent. And this kind of cyclicity activity of these things gives rise to the sedimentary packages that we talk about in sequence stratigraphy. And the factors that we just talked about, the subsidence, sea level changes, and sediment supply, I'm going to say these factors affect sediment wherever it occurs. Of course, that's not true. That statement is true when you're dealing with marine continental systems. If you're up on a continent, subsidence and sediment supply are important players. I guess sea level is of interest because if sea level drops over here in the middle of the continent, that will have an effect because of downcutting of rivers and things of that kind. But obviously, sea level is of less importance in the mid-continent than it is on margins of companies. So, to get the best appreciation, if you will, for the effects of these processes, you're best doing it where you have a standard reference. Where you have a standard of reference, and that standard of reference obviously is a shoreline. And what I plan on doing for a little bit today, and then on Monday we go through some of the settings in a sequence stratigraphic sense to show how the interaction of these various factors produces different packages of sedimentary materials. And you should all be familiar at some level with this kind of diagram, where we look at there's a hierarchy of stratigraphic cycles that we deal with, and obviously in the upper part of the diagram we are looking at a very large scale cyclic event. Major changes in shoreline position, obviously, and here coming down in this direction to the lower part of the diagram, we are looking at progressively smaller and smaller packages of sedimentary material responding to different scale issues. So at the small end of sequence stratigraphy, we have these things called parasequences, and these are the products of short-term interactions, because we deal with very small thicknesses and areal extent here, obviously. These are short-term interactions between sediment supply, accommodation space generation, and amplitude changes in sea level. Okay? And so these units, parasequence units, range from a meter to a few tens of meters in terms of their dimension. And of course, the geometric packaging that you see here is related to which of the three parameters is playing the game. So, for example, in this case, if you hold sea level constant at this point right here, and you can, as we say, you can hold the sedimentation rate constant also, but if the sedimentation rate exceeds the accommodation space generation, then you'll end up with a progradational package developed like this, in which the offshore marine deposits shown in gray, shallow marine littoral package sediments shown in the darker yellow, and alluvial and coastal plain pseudo-continental type deposits shown in the tan color, so that if you punch a hole in that sequence, you get a little parasequence, which is a coarsening upward sequence, which is what you get with progradation, obviously. Well, no. If you keep sea level,
for example, the shoreline.
The shoreline will be there. Okay. If we run the clock forward, here is your accommodation space. Okay. Sediment being supplied in this direction will cause the shoreline to migrate in this direction.
And shoreline will be like this. Not really. It shows like not really. Not really.
Or aggradation, of course, will occur when sea level or relative sea level and sedimentation roughly matches. Then you will get an aggradational cycle. Here, what we're saying is sea level is constant, but the sediment supply exceeds that, and so you will have sediment here, and you begin to fill in the accommodation space, and that's why the shoreline will migrate seaward. Okay. So in this example, this was kind of like the first picture we drew. If we now change sea level, in this case we increase sea level, what will happen when you do that, you will push the shoreline landward, okay, to get a transgression, assuming that the rate of sea level rise exceeds the rate of sediment supply. Again, if you match these things, you match them exactly, aggregation is what you typically want to see. But if you don't match them, then one thing becomes dominant. So a rapid rise in sea level will push the shoreline this way, okay? But then if you then terminate sea level rise at about that level, then the sedimentation will take over and you get another progradational event giving rise to what you see here, and then you have the package, and this is the two-power sequences where you've got a coasting upward and another coasting upward cycle, and this surface then represents the rapid deepening that occurs when the sea level change is relatively rapid. Yeah, it's true. If things are balanced, then that won't occur, obviously. So when sea level rise ceases for whatever reason, whatever causes the rise in the first place, a new power sequence will develop and prograde out over the initial power sequence in an attempt to fill the newly generated accommodation space. Scale is important here, obviously. Power sequences can be deposited over tens to thousands of square kilometers. Obviously, this is in part going to be controlled by the nature and geometry of the sedimentary basin, the geometry in a geographic sense, not necessarily in a cross-section sense. And the other thing to remember, of course, is that power sequences contain a record of a variety of environments of deposition. Okay, so if we look, we've got two power sequences here, and in this particular power sequence, we are dealing with a shoreline type set of environments, offshore, shore face, foreshore, backshore environment. Here we've got another power sequence that is related to South Lake. So within these packages of sediment that form in these different settings, you can have significant changes in the larger environmental picture. So kind of a coastal beach type setting here and a delta. And if you think about that, if you go from the Brazos River mouth and come along the shore towards Galveston, the power sequence sets that are forming in those two settings will have represented in the sediment accumulation there significantly different environments of deposition. So with time and variations in sea level changes, you get power sequence sets forming. Retrogradational power sequence sets will form when you have the fairly rapid rise of sea level that overwhelms the sediment supply, and then you backfill it with progradational packages when sea level stabilizes, or the rate of sedimentation is changed, increased for some reason. Because this is always a balancing act between sediment supply and accommodation space development. So the diagram that we see there, and this thing right here, shows the effect of power sequence sets developing where you have retrogradational packages. And what you see happening here is this geometry that you see developed here is related to the fact that you have a series of sea level changes, rises in this case, relative sea level rises, of different magnitudes. And as those magnitudes increase, obviously you develop this retrogradational sediment set. This also is a product of retrogradation, but here you've got a fairly uniform rise in sea level, giving rise to, again, a retrogradational stratigraphic package, but it looks somewhat different from the one on the left, simply because the one variable that we're looking at here, sea level change, is not uniform in that diagram, it's uniform in this setting here. And this gets back, I think, to your question. I'm not sure that it does, but you will get aggregational power sequence sets developed when the sedimentation rate roughly matches the sea level change that we see in this diagram. So in this case, obviously, the shoreline does move significantly, and that's the definition of an aggregational sequence only. And this shows an aggregational sequence set over some period of time where we have uniform rates of sea level rise that is roughly matched by the sediment supply. Again, the point here is that the shoreline, which is marked somewhere around here, essentially remains in place. And then we get back to the point that we were making earlier. Progradational power sequence sets would form when the supply of sediment outstrips the rise of sea level. And again, the thickness of the power sequence sets will in part be related to the change of sea level and the rate of sediment rise. On the right-hand side, a sequence of events where we have a different progradational geometry, slightly different progradational geometry related to different sea level changes. When you don't, here we've got a situation where we have significant progradation where there is no change in sea level. This is what sometimes I think is referred to as a depositional regression, because the supply of sediment pushes the shoreline seaward. You have a similar effect here with progradation, but in this case we have a lowering sea level in addition to the oversupply of sediment, as it were. And when the accommodation space decreases because of the fall in sea levels, is what we're seeing here, that's what's referred to as a post-regression that was asked about earlier. So you've got the two kinds of regression here. You've got the depositional regression and the post-regression. Okay. It's sometimes called a normal regression, yeah. Looks like what? Well, I mean, progradation exists to the extent that as the sea level drops, I mean, the shoreline has to go with it. I mean, it has no choice in that sense. But so the shoreline is moving seaward, which is the definition of a regression, and what we're saying is this is a forced regression because of the sea level, relative sea level change. This example, the shoreline also moves seaward, and so it's a true regression, but it is the product of the effect of deposition, and hence the the term depositional regression is sometimes applied to it. Okay, so the force regression is independent of sediment supply. It's related purely to the lowering of sea level, because conceivably you could have a lowering of sea level where you had a very poor source of sediment back there and you're not supplying much sediment anyway. The regression still occurs. In this lower one? I'm not sure where you get the aggregation package there. Oh, okay, yeah. And the other thing that happens, of course, in this aspect of the force regression, the shoreline moves to a lower level on the depositional profile in this particular situation. Okay, let me stop there and we'll continue from there on Monday. I was looking at my calendar earlier today and I noticed that I had on the 27th, which is a week from tonight, I guess, we have the third short quiz. And that will cover material from conservative plate margins through, let's make it through material that we covered on Monday. So stuff that we covered tonight will be on quiz 4. Okay?